So, let us start this lecture with a thought process that is which is important for human life. What we call man is a thinking animal, right. So, good thoughts makes a man, while bad thoughts end a man. So, one has to be careful about his own thoughts, what are coming to you. And let us now go back to our discussion on thermodynamics. And in the last lecture, we discussed basically the gas power cycles. In that, we looked at the example of Otto cycle, what we call a spark ignition engine also, because spark ignition engine is modeled using the Otto cycle, and also it is known as gasoline engine, not only the SI engine or the spark ignition engine, but also the gasoline engine. But if you look at this, gasoline engine is being used basically for the small powers, and then as we had discussed that its limitation is the lower compression ratio. As a result, the efficiency will be, you can think of, lower. And in order to enhance this efficiency and utilizing the problems faced by that the problem faced by that is the auto ignition, right, which will be leading to the uncontrolled combustion. So, we will be now discussing an engine which utilizes that concept and developed engine, that is the diesel engine. So, we will be discussing about basically ideal diesel cycle, which is based on the air standard assumptions what we had done for the Otto cycle. Those assumptions will be valid for this ideal diesel cycle. And diesel, Rudolf Diesel is the person who devised this cycle, and also he conducted experiments in 1893, who really did not use diesel for his experiments. He used vegetable oils for that, okay, what we use today known as biodiesel. Okay. You might be aware biodiesel is a very big thing nowadays, but it is, the history goes back to the Rudolf Diesel in 1893. So, and generally this is being used very much for the trucks, buses, car, locomotives, ships, and several places, like even if you go to the rural area, we do pump the water in the field, right, for cultivation purposes, and that uses the diesel engine. And beside this, for the temporary power kind of thing, what you call the generator, kind of generating electricity, we do use the diesel. But however, the gasoline engine is restricted to very small power, like a car or a automobiles and bike, kind of things that is being used. So, and in this case, what is being done is the fuel is injected into compressed air, which ignites automatically, right. There is no need for any spark ignition engine. But in this case, if you look at that concept, the problem which was faced by the auto engine, that is the auto ignition, being exploited here to the advantage, which was a disadvantage for the auto engine, that is being used as advantages in this engine, right. As a result, we need not to have a spark igniters. In case of a gasoline engine, we need a spark igniter to initiate the combustion. And diesel engine is also known as compression ignition engine, right. The auto engine or the gasoline engine, we call it basically spark ignition engine, and here we call it as a compression ignition engine. Some place you may find CI engine, right. And just to explain it, this thing, let me just look at what is happening, difference between the gasoline. In the gasoline engine, both the fuel and air mixtures enter into the engine during the suction stroke. But in case of diesel engine, only air enters into the engine during suction stroke. You got the difference now? And then in the compression, in the gasoline engine, both the fuel and air mixture are compressed. When the piston moves up, it get compressed, and then it will spark will come and again the piston will move down, and that is of course shown here in this diagram for known as the power stroke. Okay. But in case of diesel engine, that air is compressed, not the fuel air mixture as in the case of gasoline engine. And then when it what you call compressed and the pressure will be increasing, so also the temperature. And then the fuel is injected using basically a spray, it is a liquid fuel directly injected, right. And there will be droplet, is quite a complex phenomena, spray will be there will be small droplet, larger droplets, and then there will be mixing in between, and then it will ignite off because the temperature is much higher than the auto ignition temperature. Let me emphasize again, earlier the auto ignition is a problem, but here it is a solution for igniting the mixture, kind of thing. As a result, like you can use the higher compression ratio in this case. Of course, you will have to pay a penalty. You might have observed whenever you are going in a truck and other things, that noise level is higher, and even diesel car has come up, that noise level and vibration also higher. So therefore, the life of a diesel engine is less as compared to the what you call gasoline engine. That is why the diesel engine should be made heavy little bit to absorb the what you call vibration created by the engine. So what we will be doing? We will be doing the similar cases like what we had done for the auto cycle, that is 0 to 1 is the suction without any pressure change, which is an idealization, and 1 to 2 is your compression, isentropic compression, and to 2 to 3 is your heat addition at a constant pressure. Keep in mind, this is a constant pressure heat addition, right. And in case of auto cycle, the heat addition is constant volume heat addition. Are you getting my point? So this is a very important point you should keep in mind. After that, of course, it is same from state 3 to the 4, isentropic expansion, and this is basically power stroke, because the power by the engine is being produced during this expansion process only. And 4 to 1 is your constant volume heat rejection during the suction. Of course, 1 to 2 will be constant pressure, exhaust kind of thing, which is idealization. This is the ideal cycle. Keep in mind that we are using ideal, for the simplicity. And if you look at in TS diagram, right, it looks like that. I have not considered the 0 to 1 as a process in the TS diagram, and 1 to 2 is your isentropic compression, and 2 to 3 is your constant pressure heat addition, and 3 to 4 is your isentropic expansion. Of course, 4 to 1 is your heat rejection, right. So this is the process, and we are going to analyze that, and we will do the similar way, and here again we will be considering the control mass system, not the control volume. Of course, keep in mind that you can also use the control volume and do that, but you will have to do it carefully. Okay? You do not think that only the control mass system can be utilized. You can use that, but one has to take care of it. Any problem, thermodynamic problem, can be solved either by the control volume or the control mass, but in one case it will be simpler, other case will be little complex, that is all. Here we are taking the control mass system because it will be simpler one. Okay. So the thermal efficiency is basically equal to the net work done divided by the Q in, and net work done we know that Q in minus Q out, right, that is the net work done, and divided by the Q in will give me the thermal efficiency, and we are always interested to find an expression for the thermal efficiency and also the work done. So, the heat energy added is basically Q in is equal to Q 23 into Cp 3T minus T2, right, and heat energy rejected is Q out, and which is Q Cv into T4 minus T1, right. If you look at this heat added is basically constant pressure heat addition. So, therefore, the Cp will come into picture, is not it, the change in enthalpy basically, constant pressure process you know very well, that is heat addition is nothing but change in enthalpy, Cp into delta T, that is the thing, and it is a heat rejection, and you put that thing is basically 1 minus T4 minus T1 divided by gamma, because Cp Cv if you look at into T3 minus T1. So, if you look at, you can do it here itself, that is 1 minus, that is Q out is nothing but Cv T4 minus T1 divided by Cp T3 minus T2. So, Cp Cv, this one is nothing but your gamma, Cp by Cv is your gamma, okay. So, Cp by Cv. So, if I take this out like T1 here, then I will get T4 by T1 minus 1, and in similarly in the denominator, like if I take T2 out, it will be T3 by T1 minus 1 in this bracket. So, what we will do, we know that this T1 by T2, right, we know this, what is that, right, we have already done in the your Otto cycle. We can relate this between this state 1 to state 2, this is isentropic compression, we can basically convert that into the compression ratio, right. So, we have already done that, T1 by T2 is nothing but 1 over Cr, that is the compression ratio power to the gamma minus 1. And considering the isochoric process for 1, we can get basically T4 by T1 is nothing but your P4 by P1, and I can write down P4 by P3 into P3 by P1. And if you look at constant heat addition, therefore, we can say that P3 constant pressure heat addition, right, constant pressure heat addition, therefore, P2 is equal to P3. So, therefore, I can write down P3 in place of P3, I can write down P2 here. And if you look at this P4 by P3 is basically nothing but relate the isentropic expansion, and P2 by P1 is isentropic compression process. So, you can relate that thing and then do that. So, we know that for this both the isentropic process, the PV gamma is constant. So, therefore, we can write down T4 by T1 is equal to P4 by P3 into P2 by P1, we have already seen that, and P4 by P3 for an isentropic process is nothing but V3 by V4 power to the gamma, and P2 by P1 is nothing but V1 by V2 power to the gamma. And for a what you call constant volume heat rejection, right. So, therefore, this V4 is equal to V1 for isochoric process, right. So, therefore, this V1 will be cancel it out, and you will get T4 by T1 is nothing but V3 by V2 power to the gamma. So, this we call it as basically cutoff ratio. This is what we call cutoff ratio, COR. It is basically being cut off, and then like because you are going to add process between the state 2 to 3, what you do? You add the heat, basically add the fuel for the combustion, add the heat. So, therefore, after that it is being cut off, like therefore, this is known as cutoff ratio. So, now cutoff ratio is like is equal to V3 by V2, which is equal to T3 by T2 that we have seen. And the thermal efficiency, we can look at this ratio is basically, if you look at T1 by T4 is nothing but your COR power to the gamma, is not it? And we will have to see T3 by 2, what is this one? This portion is nothing but your COR, and already we know this T1 by T2. So, therefore, we can express this thermal efficiency as basically thermal efficiency is equal to 1 divided by gamma CR power to the gamma minus 1 into COR power to the gamma minus 1 divided by COR minus 1. So, if you look at now, the thermal efficiency is function of not only the compression ratio, but also the cutoff ratio apart from the gamma. That means, one more variable has come into picture for a diesel engine, right. So, we can look at how it is varying. We can take various what you call cutoff ratios and then vary this here for a particular gamma, right. And if I take these things, cutoff ratio of 1, 2, 3, 4, you can see the thermal efficiency is basically decreasing, right, for a particular pressure ratio, whatever pressure ratio. If I take this one pressure ratio, compression ratio of 12, you can see this COR is 1 is higher thermal efficiency as compared to the COR cutoff ratio of 4, right, for a particular compression ratio. And of course, it is the similar in nature that of Otto cycle. In the beginning, it will be having higher slope as it decreases for a particular curve, and the typical compression ratio for a diesel engine varies from 12 to 22. So, that you can get a very higher thermal efficiencies. And when this cutoff ratio is equal to 1, this is the Otto cycle, okay. And if it is of course different than 1, will be a diesel cycle kind of things, depending upon that. And keep in mind that generally what you call Otto cycle operates over what you call around 8 to 10, 11 something people use even kind of things, not beyond really 12, but this engine start from beyond 12, right. So, therefore, one can say that as I told, for the same compression ratio, Otto cycle is greater than the diesel cycle, right. Then question arises, is heat addition in Otto cycle and diesel cycle model well? If you look at in the case of Otto cycle, what we have modeled? We have modeled it basically as a constant volume heat addition, right. That means what? It will be very fast process, right, because volume will not be changing. If you look at the engine is moving, right, all the time it will be piston will be moving, right. You are saying instantly it will be combustion taking place. And the diesel cycle, if you look at, it is a constant pressure process, like, right, the pressure is remaining constant, right. So, which is not really the true model if you look at, both the cases is not possible. So, we will look at that in the Otto cycle. As I told, the isocoric heat engines is the first chemical reaction should occur instantaneously, within the fraction of second. Why fraction is a nanosecond, it will be doing like that, you can think of, which is impossible. Similarly, the isobaric heat addition, which is a slow chemical reaction, will be occurring. So, that pressure will not go up, right, pressure will be remaining constant during combustion, which is not possible, because heat being added, the pressure will go up in a constant volume kind of thing. So, therefore, both the thing is not right. So, what we will do, we will have to can model basically combustion as a both combination of isocoric and isobaric heat addition. If you do, it may mimic the actual cycle to some extent. and that we call it as a dual cycle, right, where the constant heat constant volume heat addition and constant pressure heat addition can take place. So, the cycle will be looking like that. If you look at 1 to 2 compression, isentropic compression will be same, but and 4 to 1 isentropic expansion, it is the same as the either the Otto or the diesel cycle, and constant volume heat rejection all are same. Only the difference is that here we are saying it is a combination of 2 to 3, that is a isochloric heat addition, and 3 to 4 is a constant pressure heat addition. That is the difference what we are saying. Basically any engine will be combination of that we are saying, and that is the dual cycle. And the thermal efficiency, if you look at, we can find it out, basically 1 minus Q out by Q in, and that is the constant heat addition between station 2 to 3, constant volume heat addition, that is Cv 3 minus T2, and constant pressure heat addition, that is Cp T4 minus T3, right. This is the thing what will be, or of course, the Q out will be constant volume heat rejection. So, if you look at now, if I substitute this heat rejection constant volume, that is Cv T5 minus T1, and here, right, and divided by the, this is the constant volume heat addition and constant pressure heat addition. So, it is a little complex, like, because there are several temperature comes into picture, T1, T2, T3, T4, T5, like all are coming this thing, and we will have to look at how we can express in terms of certain parameters, like what you call compression ratio, cutoff ratios kind of things, so that we can vary those parameter and find out what is happening, right. So, if you divide this thing by basically Cv, here, this will cancel it out, and Cp by Cv is nothing but gamma, right. And we can express in terms of various ratio. Already we have defined the what you call compression ratio V1 by V2, and cutoff ratio V4 by V3 we have already defined, and we are defining another ratio, expansion ratio ER, right. This is, I call it expansion ratio V5 by V4, right, and pressure ratio, this is pressure ratio is equal to PR P3 by P2. Okay. So, we will be doing a little algebra to express this thermal efficiency of various things. So, we know that ER, that is expansion ratio, is basically V5 by V4, and I can write down basically V5 is equal to V1 here, right. V5 is equal to V1 because of isochloric heat rejection. So, therefore, I can write down in place of V5 V1, V1 by V4, and I can also write down V1 by V2 into V2 by V4, and V2 is nothing but your V3 isochloric heat addition, right. So, therefore, this is the process if you look at. So, therefore, I can write down basically V1 by V2 into V3 by V4, and we know that this is V1 by V2 is nothing but your CR, yes or no. See, this is your CR, and V4 by V3 is nothing but 1 by what you call COR. So, ER is equal to CR by COR, right. And if you look at the cutoff ratio, that is V4 by V3 is equal to T4 by T5 into P3 by T3. and we know that P4 is equal to P3 for a constant pressure heat addition. So, therefore, that becomes, this will cancel it out. So, therefore, that becomes T4 by T3, and therefore, we can what you call express the T3 in terms of T4 by COR, because now we are expressing this thing, and keep in mind that what we will be doing, all these temperature we will be expressing in terms of T4, right, in terms of T4. So, for the process 2-3 is nothing but P2 by T2 is equal to P3 by T3, because it is a constant volume heat addition between the state 2 to 3. So, therefore, we can write down T2 is equal to T3 into P2 by P3, and already we know the T3, right, that is your T4 by COR, and this one is nothing but 1 by PR by definition, pressure ratio, right. So, therefore, we are now getting T2 we are getting, right, in terms of T4. Similarly, for the process 1 to 2, we can get T1 divided by T2 is nothing but V2 by V1 power to the gamma minus 1 is nothing but 1 over CR gamma minus 1, right. That we have already done for the both the what you call for the Otto cycle, right. And that is nothing but basically T1 is equal to T2 into V2 by VR. I mean, like, then you can express this T1 in terms of compression ratio. And if you look at the T1, right, because already we have calculated here T2, T2 is nothing but your T4 by COR into 1 over PR, you just substitute these values here in place of this, and you will get, you are expressing T1 in terms of T4 and cutoff ratio, compression ratio and PR, right. Basically, what I am trying to do, expressing all the things here in terms of T4, right. So, T1 is already we have done that, I am like so for the process 4-5 I can get T5 by T4, right, is equal to V4 by V5 power to the gamma minus 1. Already we have defined this is ER power to the gamma minus 1, and we know that ER is equal to basically V5 by V4, and if you look at, I can say that V5 is, what is V5? V5 is equal to V1, right, isn't it? Because that is the your constant volume heat addition. So, therefore, V1 and divided by V2 I can say, and V4 by V3 and V2 by V3 is same for the constant volume heat addition, right. So, that is nothing but your what you call CR, this is by definition, and V4 by V3 is nothing but your COR. So, therefore, I can express the T5 in terms of T4 e power to the R, nothing but this thing for ER is equal to CR by COR. Therefore, you can put these values here. Again, we are expressing T5 in terms of T4 and other ratios. And already I think we got this T3 is equal to T4 by CR, and T2 already we got that T4 by COR into 1 over PR. So, if you substitute these values, what you call T5 here, right, and T1 already we know, right, T1 is here, right, and T3 and all those things we have expressed. If you express that thing here, right, and simplify it, you can get basically is equal to 1 minus 1 over CR power to the gamma minus 1 into COR, that is cutoff ratio power to the gamma, into PR pressure ratio minus 1 divided by the PR minus 1 plus gamma PR into COR minus 1 in this bracket. So, if you look at in this process, we have reduced one variable, right, which we had defined, that is expansion ratio is not coming in this expression. So, therefore, if you look at apart from the CR and cutoff ratio and gamma, there is another variable which has come into picture in case of dual cycle, that is the pressure ratio, right. So, one can do that and then express it kind of things. So, we will be I mean like you can see that this will be trying to mimic the actual cycle to some extent, not real to the greater extent, but however it is better than this. This is known as a dual cycle. And keep in mind that the second law of efficiency, second law of efficiency is basically equal to the dual cycle by the Carnot cycle. This is your Carnot cycle efficiency, Carnot cycle efficiency. This will be not only true for the dual cycle, it will be true for the Otto cycle, diesel cycle and other cycles as well. Are you getting my point? So, you please keep in mind that, and that will be helpful to know how much we can extend the thermal efficiency if it is less than the what you call second law of efficiency. If it is equal, then you cannot go, and that means that will be the reversible engine. Okay. So, that will be very important one has to look at whenever you are doing cycle analysis, one can also look at the second law of efficiency of the cycle. And now, what we will be doing, we will be looking at another cycle which is basically used for the what you call gas turbine engine, and then it is known as the Brayton cycle. And George B. Brayton found out that thing in 1870. If you look at all the cycles are in similar, all the engines are on the very narrow band periods in the history, and all are developed simultaneously. Like during our independence time, like era, a lot of great people come up in this country and who have got independence, but after that there is a lull, right. So, before that also there is a lull. So, that is the kind of things what happened during that Renaissance period we call, and it basically these gas turbine engines find application in aircraft, power generations, even the ship, like for propelling a ship, big ships and other thing. And gas turbine generally operate as an open cycle, right. And if you look at, it is having a component of a compressor, like it is similar way you will have to compress the air or the gas air from state 1 to the 2, and then there will be some combustion, combustor will be there. This is basically a combustors which will be modeling it as a heater, because we will be doing air standard analysis, and then it will be expanded in a turbine which will give me the work, right. If you look at this, will give me the work, right, and this work also supplied to the compressor, because the work from the turbine will be supplied to the compressor, so that it can go, because you will have to supply work to the compressor. But what we will be modeling it as basically a closed cycle, although it operates on the open cycle, right. We will be saying that look, the heat rejection will be taking place a cooler, and so that it will be closed, and we will be modeling it as a closed cycle, right. And air standard cycle, that means in the combustor is replaced by a heater, as if combustor is external, and keep in mind this is known as also a internal combustion. Combustor is a part of the engine, but in this case we are saying look, it is away, it is giving only the heat for this our analysis. So, I have already shown you this picture, again I am putting it. So, if you look at this is your what you call compressors, of course there will be a low pressure compressor, high pressure compressor, anyway it is a compressor, and this is your combustion chamber, it is a very tiny one, if you look at this is your combustion chamber, and then it is expanded in the turbine, these are all turbines, and you will get the, of course, in this engine, like you can get the power, and then particularly this engine is meant for the getting the thrust, and it is the gas has to be expanded in a nozzle. Okay. So, in case of power generation, you need not to have a turbine, all expansion will be taking place in a turbine. So, you need not to have a nozzle, all the expansion will be taking place in a what you call turbine, so that you can get work done. So, as you know from here, the air will be entering in this place, and then it will be, fuel will be burnt over in the combustor, and it will be expanded in turbine, it will going out, the product gases, right. And this is basically an open cycle one can think of, but we are modeling it as a closed cycle. So, let us look at the processes, I mean like processor 1 to 2 in TS diagram. This is a isentropic compression, right, entropy will not be changing, and 2 to 3 is your constant pressure heat addition. It is similar to that of your what you call diesel engine. And 3 to 4 your isentropic expansion, and 4 to 1 is your constant pressure heat rejection. Okay. In case of diesel engine or auto engine, the heat rejection is constant volume, but in this case constant pressure heat addition and constant pressure heat rejection, that is the difference. So, you can see that thing in the process in the PV diagram, it is very clear that heat addition in this case is the constant pressure, and heat rejection is the again in the constant pressure, unlike the diesel and auto cycle, that heat rejection. So, we will be looking at the again thermal efficiency, that is equal to 1 minus Q out divided by Q in, and in this case the heat energy absorbed is basically change in enthalpy. Now, in this case what you will be using? Will you be using control mass system or control volume system? What is the natural one? You can use both, as a matter of fact. What will be natural one? Natural one will be control volume system. Okay. So, therefore, the Q in is basically change in enthalpy, right, that is nothing but Cp T3 minus T1. Keep in mind that we are considering the Cp as a constant, it is not a function of temperature, but in real situation it is not, it will be function of temperature. Okay. But in ideal cycle or air standard cycle is like that. So, heat energy rejected is nothing but Q out, that is Cp T4 minus T1 here, right, and then we can get the net work done is basically the turbine work minus the compressor work, right. So, that is turbine work Cp T3 minus T4 and compressor work Cp into T2 minus T1, this process, this is your compressor. So, the net work will be basically Cp T3 I can take out, then I will get 1 minus T4 by T3. Similarly, in the compressor part I can take T1 out, that will be then in the bracket it will be T2 divided by T1 minus 1, right. And for isentropic process 1 2 we know T2 by T1 is equal to P2 by P1 power to the gamma minus 1 divided by gamma. And this ratio what we call is basically compression ratio, you can say that this is the compression ratio what we call, and we call it based on the pressure. So, I will be defining this as a PR, okay. And that is different in case of auto engine. Auto engine basically based on the volume, in this case based on the pressure, that is the difference. Okay. So, let us, as I told that it is the PR I am defining for isentropic process, and that is true for also the expansion process. So, therefore, we know P 3 by P 4 that during the expansion process is nothing but your what you call pressure ratio, and P 2 by P 1 also during the compression process between state 1 to the state 2 is also known as the pressure ratio. Keep in mind the pressure ratio always defined from the higher pressure to the lower pressure, that we have defined for both the compression and expansion. So, therefore, we can write down the T 3 by T 4 power to the gamma divided gamma minus 1 is equal to T 2 by T 1 power to the gamma divided by gamma minus 1. So, therefore, we can write down that what you call T 3 by T 4 is equal to T 2 by T 1, and we can write down that is nothing but your what you call I can take this what you call temperature over here and the temperature T 3 to this side, then I will get T 4 by T 1 is equal to T 3 by T 1. So, we know that T 3 by T 4 right is equal to P 3 by P 4 is equal to P r power to the gamma minus 1 divided by gamma, which is nothing but by T 2 by T 1, right. So, therefore, we can write down like this expression. If you look at T 4 by T 1 minus 1 can be cancel it out T 3 by T 2 minus 1 as this is the case, right. So, it simplifies, it says that the thermal efficiency is basically equal to 1 minus 1 divided by P r gamma minus 1 divided by gamma. This is similar to that what we got for the Otto cycle, right, similar, it is not same. So, therefore, for a particular gamma P r will go up, the thermal efficiency will be going up, it will be increasing. And if you look at the typical pressure ratio for this is something 5 to 20, even people are using the pressure ratio of something 35 to 40 even nowadays people are using very. But as you go on, then turbine inlet temperature will be very higher because you are using higher compression ratio, and then there will be limitation of the what you call material and heat additions kind of things. And but very important thing what I would like to draw your attention that back work ratio in this case is very high, right. If you look at the something the 60 to 70% of the turbine work is utilized for pumping the gas in this case, whereas for a what you call steam power plant we have seen something 1 to 2% is negligibly small power is being utilized for pumping purposes. So, therefore, that you should even kind is basically guzzling that compressor is guzzling lot of power. So, we look at the question arises what will be the pressure ratio we should use so that maximize the work output, and for that we have already derived this expression. And we can also express that in terms of pressure ratio, right, because we know T 3 by T 4 is equal to pressure ratio power to the gamma minus 1 is equal to T 2 by T 1. This we have already derived. So, then I can write down this expression in terms of T 4 by T 3. If you look at this is nothing but 1 over power to the P r power to the gamma minus 1 divided by gamma, right, this portion. So, this portion is nothing but that, right. And a similar way we can also find out basically T 2 by T 1, this one is equal to this portion, right. And then what we will do, we will have to find out what is the maximum pressure one can get, so that my net work output will be maximum. That means, what is the pressure ratio I should use so that I can maximize my work. So, what I will have to do? I will have to basically differentiate this expression with respect to pressure ratio, and that is equal to 0, right. We can do that, And so, for maximum, as I told that we will have to do this net work with respect to the pressure ratio, that is a 0. Of course, you can keep the temperature T1 constant and 3T is basically T3 is constant, you can consider. So, if you do that, you will get this expression, and it right, and you will get this P r power to the 2 minus 2 divided by gamma is equal to T3 divided by T1, and so that we will get an expression that maximum pressure ratio, what you can do is basically T3 by T1 power to the gamma divided by 2 gamma minus 1. And as I told that if I increase this T3 here, if you look at this T3 will be higher, then naturally the work net will be higher, because if this T3 is higher for the rest of the things, then naturally net work output will be higher. But however, there is a limitation of the limitation of increasing this temperature, because the turbine inlet material, is a problem, because the turbine will be subjected to what you call not only the thermal stress, but also the centrifugal stress. So, therefore, if I say this turbine material is basically limited to 1700 Kelvin, then we can find out what will be the pressure ratio. For this example, if I put this is 1700 Kelvin, right, and 300, you will get, I can get maximum pressure, we can operate the pressure ratio at 20.8 for getting the maximum work output. By this we can optimize, like find out what is the pressure ratio one can operate, and if I am getting a lower turbine inlet temperature, then naturally I will have to go for lower pressure. If I increase this one to the higher like values for with the advent of better material, then naturally I can go for the higher pressure ratio. So, what I am saying, by using this simple cycle, you can really play around and find out ways and means of doing the what you call enhancing the thermal efficiency. As I told earlier that in case of vapor power cycle, right, that you can regenerate, you can kind of things. So, here also you can do the regenerative kind of things, you can recool, you can compressor work you can reduce, because here in gas turbine engine the problem is the compressor is guzzling the power, is taking all the power out. So, therefore, you can cool it during the compression, this is known as intercooling, you can do that, so that you can reduce the work input to the compressor, and as a result you can increase the net work output, and then thermal efficiency of course will be increasing. There are several ways and means which is not a part of your course, but I am just trying to give you a flavor. There is a lot of scope for improving the what you call performance of the engine by using simple cycles. And of course, there will be realistic cycles, like in this case one can think of what you call using the isentropic efficiency, what we had done earlier, right. We had used some isentropic efficiencies, right, for the compressor and expansion. By that we can also analyze the real cycles, not only for the Brayton cycle, but also for the what you call Otto cycle, diesel cycle, other things. Okay. So, with this I will stop over here, and then next class we will be looking at refrigeration cycles. Thank you very much.